Boys on.
Go for engines.
7, 6, 5, 4, 3, 2, 1, 0, and liftoff.
This is the Space Shuttle Atlantis on July 8, 2011, taking off for the last time from the Kennedy Space Center, marking the end of an era of many advances and research across several fields, especially in space exploration. After that flight, 11 years would pass without NASA launching any rocket of its own. That was until a few years ago when the first rocket, the SLS, which had been under construction since 2011, was finally assembled inside this building, called the VAB. More than 6 years behind schedule and a budget overrun of more than $2 billion and facing all kinds of difficulties. But difficulties aside, this is the largest, most powerful, and most expensive rocket currently entering operation. $23 billion were spent during its construction, and thousands of people worked hard to make it a reality, being the key piece of the so-called Artemis program. A set of 3 flights will put the first woman and also the first non-white man on the surface of the moon by 2024, in addition to exploration, collection, and carrying out various scientific experiments on the lunar surface. All of this will happen within this decade, thus establishing the first long-term presence on the moon. The SLS, or Space Launch System, is an American super heavy lift rocket designed for deep space exploration, that is, beyond Earth's orbit. For destinations like the Moon, Mars, Jupiter, and Saturn, the SLS is, as NASA itself calls it, the most powerful rocket in the world, capable of carrying much heavier and much larger payloads, and even taking astronauts directly to the moon in a single launch. The SLS is made up of several parts and subparts, but it basically consists of the following main components: the core stage or main stage built by Boeing, 2 solid fuel side boosters, the interim cryogenic propulsion stage, or ICPS, which is the rocket's second stage, the Orion capsule where the astronauts go, and the launch abort system, which is a small solid fuel motor at the tip that takes the capsule containing the astronauts far away in case of serious problems, such as a rocket explosion. This system is the fail-safe that will save the astronauts' lives if everything else fails. But let's get into the details. The core stage is a gigantic fuel tank, 64.6 meters tall and 8.4 meters in diameter. This monstrosity stores 2 million liters of liquid hydrogen at temperatures of minus 252.7 degrees Celsius and 741,941 liters of liquid oxygen at minus 182.7 degrees Celsius, totaling 2,763,000 liters of fuel on board. And incredibly, all this fuel is consumed in just 500 seconds, or a little over 8 minutes. Empty, it weighs 85.2 metric tons. And that orange color is actually a special foam that's applied and serves as insulation because of the super-cooled propellants inside. This tank also houses the flight computers and many of the avionics needed to control and guide the rocket during flight. This tank is made of 2219 aluminum. Underneath this tank is where the 4 engines of the SLS, the RS-25, are mounted. These are the same engines used on the space shuttles with minor modifications. These engines have already flown on the space shuttles before, so they're not new. Some of the modifications made to these engines include a new engine controller, new nozzle insulation, and changes so that it produces 512,000 pounds of thrust, unlike the previous 418,000 pounds at sea level on the space shuttles. During flight, the 4 engines together produce about 2 million pounds of thrust. The other part that makes up the SLS are the 2 solid fuel booster rockets on both sides of the rocket. These boosters are derived from the space shuttles and will provide just over 75% of the total thrust needed for the vehicle during launches. Northrop Grumman, the company that developed the original boosters for the space shuttles, made changes so that these boosters would meet the requirements performance, and operations needed for the rocket. SLS, including changing the original 4-segment fuel design to the current version with 5 fuel segments. These boosters use solid fuel, more precisely a mixture of these two. A booster like this burns 5 tons of fuel every 6 seconds, and they work for about 2 minutes. And if the space shuttle boosters could parachute down to the sea to be recovered, in this case that won't happen since the entire parachute system was eliminated from the design. The other piece is the ICPS, or Interim Cryogenic Propulsion Stage, which is the second stage of the SLS. Built by Boeing and United Launch Alliance, it is 13.7 meters tall and 5.1 meters in diameter. This stage uses liquid hydrogen and liquid oxygen and has only one engine, the RL-10, developed by Aerojet Rocketdyne, capable of delivering 24,750 pounds of thrust. This is the stage responsible for propelling the Orion capsule to lunar orbit after the side boosters, as well as the core stage, are separated from the rest of the rocket. The ICPS is actually a modified version of the cryogenic second stage used in the Delta IV rocket family. The modifications made to it for the SLS include a larger liquid hydrogen tank, the addition of hydrazine bottles for attitude control, and small changes in the avionics, and a liquid hydrogen vent valve that allows the engine to be reignited in flight. And as you can imagine, an engine is necessary. A lot of extremely sophisticated computers, or as they're called, avionics, are needed to control this whole machine that vibrates, spins on its own axis, turns, reaches speeds of about 28,000 km/h in just over 8 minutes, and consumes absurd amounts of fuel every second. And besides that, there are 2 types of fuel being burned at the same time: liquid in the core stage and solid in the booster rockets. And to make things worse, the 4 engines of the core stage have a gimbal mechanism, which allows them to move freely during flight to make adjustments and corrections to the vehicle's trajectory. In other words, the computers are critical components in this whole system. Some of them are located in the boosters themselves, specifically in this part. The avionics in the boosters control all the operating and functioning parameters of the booster, but they are in constant communication with the main computers in the core stage. In other words, the booster computers only execute what the core stage computers tell them to do. So instructions to ignite the boosters at launch or to move the exhaust nozzles to a certain position are sent by the computers in the core stage. And speaking of the core stage, a good part of the entire electronic brain of the SLS is in it, including the inertial navigation unit, sensors, and the 3 flight computers, of which at least 2 must be working properly during the flight. However, one alone cannot control the rocket. But I'll let Elisa Mitchell explain the SLS computers better. The SLS computers.
These are boxes that are just like the ones that will go on the rocket, but they are not the actual flight boxes. These will never fly on the actual rocket. We connect them into the system because it's the first time they've ever been integrated with other flight boxes, so we can see or determine how the rocket will actually fly. We can add winds, we can add rain, we can add all kinds of different things. Because we have hundreds of models, we can simulate different environments. Essentially, the models show us how something is going to behave. We can even command one of the flight computers to shut down and see how the rocket performs with the remaining 2.
There are 26 avionics boxes in total, and because of the complex nature of rockets. Since it's a new vehicle, issues could arise that might compromise it. Problems were practically inevitable on the first launch, with the first 2 launch attempts ending in cancellations. On the first attempt, which took place on September 1st, one of the 4 engines of the core stage, specifically engine 3, did not reach the required temperature. The RS-25 engines are continuously cooled and kept that way until ignition. This is done by allowing liquid hydrogen at minus 252.7 degrees C to circulate through various engine components, including the turbopumps, exhaust nozzles, and other parts, keeping them cooled until ignition. But on that day, a valve that allows liquid hydrogen to flow to Engine 3 didn't do its job as it should have. The engine didn't cool properly, causing the launch to be canceled. On September 3rd, during the second launch attempt, another problem ended up canceling the launch again. This time, a leak in the fuel line, specifically a line that carried liquid hydrogen to the rocket, ended up compromising the launch attempt. They tried 3 ways to solve the problem, but without success. It was believed that the rocket would be taken back to the VAB for repairs. Also, because the FTS, or Flight Termination System, which is mandatory, was installed for that purpose. If the vehicle goes off course and becomes unstable, it can be destroyed. Its batteries would eventually run out, making it necessary to recertify the entire system. And the FTS is located in an area of the rocket that is only accessible in the VAB. But a NASA statement from September 7th said that the repairs will be done with the rocket on the launch pad without the need to take it to the VAB, which increases the chances of a launch happening very soon. But the fact is that the SLS is an advanced rocket and carries the weight of a noble mission. A lot of technology, techniques, principles, and even mistakes made in the Apollo program, as well as in the space shuttles, provided lessons that were applied in the design process and in the engineering of the SLS itself. All of this made it possible to design a rocket 100% focused on crew safety and with a greater payload capacity beyond Earth's orbit. That's why more than 90% of the SLS is completely discarded. The side boosters, the gigantic orange tank, the 4 engines, the second stage, all of that will be discarded with every new launch. But in return, you get a much greater payload capacity than ever seen before. This design philosophy also allows the rocket to be much simpler, since everything that is reusable adds weight and complexity to the project, precisely because it can be reused multiple times. And things get even worse when the highly corrosive ocean water is added to the equation. But that's it. Now we just have to wait for the launch.